Hey, welcome back to another video with Professor Smith. Today I will be talking about applications of the normal distribution. And as you can see in this first image that I borrowed from your author, we have three different normally distributed variables with given means and standard deviations. And each one of these variables, as you can see in these three z-score formulas, are being standardized or transformed with our z formula into a standard normal distribution so that we can use our table and find areas under the curve. So in our first example, I have a normally distributed variable with a mean of 28 and a standard deviation of 3. And I would like for you to find the area under the curve to the right of 30.2. Or rephrasing, that's asking what is the probability that x is greater than 30.2. So we need to standardize this distribution with our z formula to turn it into a standard normal distribution. And so we take our x value of 30.2 and we subtract the mean of 28, and we're going to divide that difference by the standard deviation, which was given as 3. So that gives me 2.2 divided by 3 is equal to 0.73 repeating. But in order to use my z table, I need to only use 2 decimals. So by calculating that z-score, I have transformed the probability that x is greater than 30.2 into the probability that z is greater than 0.73. But I don't want to do any math, so I'm going to horizontally rotate that image and look for the value or probability, I should say, that z is less than negative 0.73. So I'm going to pull up my, okay, I fixed that technical issue. So now I need to get my row highlighter down to negative 0.7, and my column highlighter needs to move to 0.03, and you could barely see it on the bottom of your screen, but it is there. The intersection of negative 0.7 and 0.03 is 0.2327. So the requested area under the curve is 0.2327. That is the area under the curve to the right of 30.2 in this normal distribution, or to the right of 0.73 in a standard normal distribution. Okay, we are going to do another problem with the same mean and standard deviation as the previous, but now I'm looking for the area under the curve between 27 and 31. So that will require that I standardize both of my z-scores. So this first standardizing is going to come from the x value of 27, and the second will come from the x value of 31. So when I have an x value of 27, that's the first number that goes into my subtraction, and I subtract the mean from my given x value, and I need to divide all of that by the standard deviation, which was given as 3. Nice of it to take my underline. So that's going to be negative 1/3 or 0.3 repeating. To use my z table, I'm going to have to call that 0.33. Oh, and I almost forgot my negative sign. For the second x value of 31, I also need to standardize that and take 31 minus the mean of 28 and divide that difference by the standard deviation, which was given as 3. Turn my underline off, but it still came through. So 31 minus 28 is 3 divided by 3. That's telling me that my z-score is equal to 1. So I have two standardized values of negative 0.33 and 1.00. So I can use my table to find the areas under the curve of being left of 1.00 minus, whoops, minus, that's silly that it keeps putting a smiley face in there, but I'm okay with it. Z is less than negative 0.33. So I'm going to take the big area minus the little area to get the between area. So the area to the left of 1, when I consult my handy dandy Z table, is, I have to go to 1.0 on the positive side and 0.00 also. So, oh, one of my favorites, 0.8413 is the intersection of this row and column. So the answer that I'm looking for here is 0.8413 minus the area to the left of negative 0.33. So we need to move our row over to negative 0.3. And since that's not going to be in the view, I'm going to put my column already in 0.3. So that when I scroll down, I can move my box down to negative 0.3 intersected with 0.03 for an area under the curve of 0.3707. So performing that subtraction, I get an answer of 0.4076. I put a little circle around it. And there is my solution. It looks like I've got a little bit more for you. I have an example again from Mike Sullivan's 5th edition, interpreting the area under a normal curve. So he tells us that giraffe weights are normally distributed with a mean of 2,200 pounds and a standard deviation of 200 pounds. This would be the mean and standard deviation of all the giraffes, and therefore these are population parameters, mu and sigma. So he asks us to draw a normal curve with the parameters labeled. That is, center it at 2200. Then he asks us to shade the area under the curve to the left of 2100. And he says that the area under the curve to the left of x equals 2100 is 0.3085 and asks us to provide two interpretations. So in his slides, he provides us with the requested picture, and we need two interpretations. So the first would be that the probability that a randomly selected giraffe weighs 2,100 pounds or less is 0.3085. Or another interpretation would be that 30.85% of giraffes weigh 2,100 pounds or less. And I have one more example from my buddy Mike Sullivan. So it's known that the length of a certain rod is normally distributed with a mean of 100 centimeters and a standard deviation of 0.45 centimeters. Suppose the manufacturer wants to accept 90% of all rods manufactured. Determine the length of rods that make up the middle 90% of all steel rods manufactured. This is a great question as a segue to the next topic that I'll be covering, which is confidence intervals. So pay attention here. It's coming back in chapter 8. So he gave us an area under the curve of a middle 90%, indicating that the remaining 10% is not in the middle and therefore has to be equally divided into each of the tails. And that's where he got the 0.05 or 5% because the normal distribution is symmetric about the mean. That translates to the same thing happening on both sides. So he has his first piece of information given as the first z-score separating the bottom 5% of the area under the curve is negative 1.645. And the second z-score separating the top 5% of the area under the curve is 1.645. We'll go over this in more detail in chapter 8, but for now, just take it for face value. He then introduces the algebraically modified z-score formula that solves for x instead of z, because we have our mean and our standard deviation, and he gave us the z-score separating the bottom 5%. So the shortest rod that should be accepted in this manufacturing process is 99.26 centimeters. Then he also calculates a second x value corresponding to the positive z-score given, separating the top 5%, and the maximum length of rods accepted in this manufacturing process should be 100.74 centimeters. And that's all, folks. I hope you enjoyed my video. Don't forget to like and subscribe. Until next time, this is Professor Smith.